Again, de Broglie hypothesis says again, all material particles have got wave behavior, am I right? Whose lambda is equal to h by p. Now again, if you ask what kind of wave it is, we don't know, isn't it? And again, it's not a mechanical wave, it's not an electromagnetic wave, it's not the kind of sound wave. That's why we call it matter wave, since we don't know. Is that okay? And one more thing is, this mvr is equal to nh by 2 pi, not mvr is equal to nh by 2 pi. I'll go to what you call Bohr-Sommerfeld quantization. I hope that's equal to p dq, am I right? P dq is equal to nh. And again, so the same can explain what you call, so E is equal to nh nu in case of so linear harmonic oscillator. Our Planck's idea, okay? The same equation can explain that one also, okay? So now look at here. One more thing is, so this also helps us to prove many quantization rules actually, Bohr-Sommerfeld quantization. Or let me take before that one, you have MER is equal to nh by 2 pi, and later you got again wave behavior of what you call material particle, lambda is equal to h by p. Remember, again, this gave some idea. This gave some quantization, okay? So this gives some idea that yeah, material particle behaves like a wave, it undergoes interference and diffraction. But these are not a framework of the theory. Is that okay? So these are not governing rule. We need more fundamental governing rule here, just like Newton's second law, where you can apply Newton's second law anywhere, isn't it? We need more governing rule. These are not governing rule, remember. So again, this is a hypothesis. This is a kind of postulate, isn't it? So this is a kind of postulate. Now you can't apply those things for any situation. You may find only energy eigenvalue, isn't it? So you will not get any other information here. Superposition of state, that kind of more information that quantum mechanics might, again, our microscopic things might be playing. Yes.
Sir, after proving the hypothesis from the Debian-Zermer experiment, so is it like hypothesis again or something different?
No, that is true. That is true. It has a wave behavior.
Yes.
Again, it will undergo interference and diffraction.
So is this a hypothesis after?
But what is that wave behavior? That we don't have much understanding. What is that wave behavior? What is that wave? Isn't it?
Nature of the wave.
Yeah. So I think after de Broglie hypothesis only, Schrodinger got some more idea. That's why they called that psi as wave function. Wave. The word wave came. Even though its use is different. Its use is to do some probabilistic interpretation. So, but they call that as wave function, isn't it? Again, so they might have dragged what you call this de Broglie idea, so to find some equation, more general equation, which explains all consequences of wave behavior. Okay, this lambda can explain only one consequence of wave behavior. What is that? Interference and diffraction, superposition, isn't it? But again, we need a generalized equation which holds all consequences of wave behavior. Just like what you call interference and diffraction also, and discreteness of energy also, superposition also, like that. We need more general theory here. So while developing that more general theory, we don't give more importance for wave picture or particle picture. Okay, while developing new theory, while developing new formalism, who cares, isn't it? Whether it is a wave or particle, isn't it? Again, we need a kind of governing rule, isn't it? We need to understand what is the law of nature. We need to understand what is the rule of game that nature is playing. Are you getting my point? We need to what you call understand, or we need to observe, and we need to catch what is the rule of the game. Look at here. Suppose I think this is also said by Feynman only. Suppose suppose you don't know how to play chess. Okay, suppose you don't know, but so couple of guys are playing the chess. You are watching that one for a long time. You can understand the what you call the rules of the game, isn't it? So like that, again, we need to find the rule. Again, now we are not understanding what nature is playing, isn't it? So these things are confusing us. Electron, which was particle for us, isn't it? Now again, look at here, it's a wave. What kind of wave, we don't know. Again, we believe that light is a what you call electromagnetic wave, isn't it? Now look at here, it's a photon, isn't it? It is quite confusing us. We don't know, we are not grabbing what is the rule of the game that is played by the nature. And our next attempt is to understand that one. After understanding, we can make a framework. We can write a game book, rule book, isn't it? That is quantum mechanics, isn't it? And why that is important? Well, again, look at here. This also gave old quantum mechanics. We call this one as old quantum mechanics. This also gave quantization rule, isn't it? Why it is important? But once you have what you call framework, so that can predict new phenomena. That framework is done using the what you call earlier experimental facts, these hypotheses and all. Okay, but that framework that can explain the phenomenon which are not explained. Not only that one, our idea is to develop the framework which can predict new phenomena. That's why we need to understand that one. That's why we are not happy with these things. So that is the next attempt. That is a double slit experiment, which is very, very important, because I'm going to code that double slit experiment throughout quantum mechanics. Whenever superposition state comes, I'm going to code that one. Okay, double slit experiment and uncertainty principle. These two are very, very important. Okay, and one more thing is I am going to put one more question. Okay, so those who have attended quantum mechanics session, Mayank, don't share that one. Okay.
Yes, sir.
Let some new ideas come out. Okay. We say microscopic, macroscopic, isn't it? Okay, that microscopic, macroscopics are relative. Can I say like this? For me, again, that big and small, these are relative, isn't it?
Yes.
For me, again, suppose this chalk-based dust, okay? So this chalk-based dust, that may be what you call microscopic, am I right? For bacteria, this chalk-based dust may be macroscopic with respect to in the perception of bacteria, isn't
So
it?
we are saying about the scale.
Yeah. So this microscopic, macroscopic, whatever we say, that is actually relative, isn't it? I mean, no, not micro. Again, we have a scale actually. Microscopic means micron, micrometer,
Yes.
like that. Okay, we have scale. Sorry, I'm not saying like that. This big and small, these are relative, isn't it? Are you getting my point? If something is very small for me, for insects or for some bacteria, those are very big, isn't it?
Yes.
Now, how do you define which is big, which is small, irrespective of this relative size, not relative size, irrespective of this kind of, how to say? How do you define, I'll generate this as a question, okay, in the assignment. How do you define big and small, irrespective of what you call writing the micro, macro, or in terms of meter? Because if you write in terms of meter, that is relatively big or small, isn't it? If you say, so 10 raised to minus 6 meter is very small for you, that's relative. Without writing this scale, because if you write what you call its what you call dimension in terms of meter, then it is only relatively big or small. You can say like that. Irrespective of that one, how do you define big and small? You have any answer? Those who didn't attend my earlier quantum mechanics class. Length around Planck, or no, again, Planck constant is 10 raised to minus 34, which is so small, okay? Don't touch that one. That's good, okay? Planck constant is also used to, because Planck constant gave the different idea towards quantum mechanics. You just read Jatili carefully, okay? So if Planck constant were 0, again, it would behave like classical. That kind of ideas are there, okay? Let me share that one. But not like that. Again, how do you say this is big, this is small? Without this kind of writing, what you call, it's a dimension. Because if you write the dimension, that is only, you can say it is relatively small. Micrometer is relatively small. For humans, it is small, isn't it? Are you getting my point? So again, for us, look at here. Suppose this bottle is big, isn't it? If you take universe, For us, this bottle is big. Suppose if you take whale, isn't it? This bottle is very small, isn't it? Then whale should define different thing. This is microscopic, this is macroscopic for whale, isn't it? No, not like that, isn't it? Without touching the relative, what you call, size, how do you define which is big, which is small? If you have any idea, try that one. Scale at which classical mechanics breaks. That's good. But there is no sharp. No, that is what we need to understand, okay? At what scale classical mechanics breaks and why actually?
So, sir, the electron particle, I mean, they also follow the Newton's law? F is equal to ma.
No, how do you verify Newton's law in case of electron? That's very important. You are quite close. Again, you try to answer later. I'll just hold that one, okay?
Okay.
Scale at which classical mechanics breaks, that is small. Yeah, that's okay. But I need some better answer. Look at here. I asked the question, what is big, what is small? You found any answer? Or again, we say for big particle we can apply classical law. For small particle we can't apply classical laws, isn't it? Isn't it? Now again, how do you quantify that big and small? How do you give the definition for big and small in an absolute way without doing any comparison? Remember, without doing any comparison, the absolute meaning of big and small we need to find. Then I think we will get our answer how to proceed with the theory. Yeah. So any answer quickly on Google Meet?
Sir, by finding de Broglie wavelength and comparing.
No, not de Broglie wavelength depends on momentum also. Okay, not only mass, size or something. It depends on momentum also. That's why you can vary de Broglie wavelength by varying velocity or momentum. So come out of that one, because de Broglie wavelength, de Broglie hypothesis, yeah, it is the motivation, but it didn't give us much idea. Okay, come out of the de Broglie idea. So we are going to use that one to say whether quantum mechanics is applicable or not later. Okay, but not in this sense. Okay, in a quite slightly different sense.
Kartik asks, sir, if measurements made on state 1, if electron is in superposition state, does measurements affect on state 2?
Measurement made on state 1 means you are saying that it is in state 1. If you do the measurement, you get state 1 only. That means you are blocking slit 2. All electrons reaching on the screen, they are definitely in state 1. Is that okay? You said measurement on state 1, isn't it? Already it is collapsed. Already it is one of the definite state. One of the possible state.
Define it.
Definite state. One of the possible state. Definite. If you close the slit 2, it is in the definite. All electrons which are reaching the slit, they are in the definite translation state. That is translation state that pass through slit 1. That's very good question.
Define it is the answer.
Yeah, definite state. It is in the definite state. Then it's again you will not observe any pattern which is because of superposition state and all. Is that okay? Similarly, if you close slit 1, all electrons reaching the screen, they are in the state psi 2. Definite state. Again, you definitely know. You don't have to even observe. Without observing, also you know that one. Yeah, it is in that state. I get your point. This is again, so only superposition state introduce indeterminacy, not a definite state. You can prepare a system with definite state. Close one of the slit. Those are definite state. Is that okay?
Electron diffraction happens through single slit.
Yeah. Wait. Again, here I have taken slit width is so small. Again, I'll talk about the diffraction little later. Okay, in case of uncertainty, there is also superposition kind of thing is happening. Superposition of different momentum state is happening. So let me talk about that little later. Okay, next session I think. Okay. Yeah. Now look at here. We say again in case of Newton's second law, F is equal to m into d square r by dt square. Yeah. Okay. This Newton's second law will never say that when it is applicable, isn't it? As long as there is a rate of change of momentum, you get again that rate of change of momentum is equal to force, isn't it? It will never say what is that mass should be. It will never say this is applicable only for small system or big system, am I right? It say as long as there exists a rate of change of momentum, there will be force. If you know the force, you can find the trajectory, you can find position and momentum accurately. Okay, let me write one dimension. Okay, so F is equal to m into d square x by dt square. Okay, I can find x as a function of t, I can find v as a function of t, or I can find p as a function of t, because which is more general. Momentum is more general than velocity, because sometimes if you take variable mass situation. Okay, now, so that's why look at here, our perception of big and small, which are quite relative, isn't it? Again, we say microscopic thing, macroscopic thing, isn't it? Microscopic is small for us, isn't it? Suppose for bacteria, for smaller creatures, that is big, isn't it? Are you getting my point? So for us, suppose this species is big for me. For again, suppose very big creatures like whale, this species is small, isn't it? Like that. This is big and small. These are actually what you call relative, isn't it? I don't need relative definition of big and small. I need absolute definition of big and small. Is that okay? That absolute definition of big and small. Look at here. And one more thing that you need to observe is, look at here, Newton's second law. It will not talk about when it is applicable. It will not talk about whether particle is big or small, isn't it? It says as long as there is a rate of change of momentum that's equal to force, isn't it? So now look at here. That's why I'll take this experiment. It's the best thought experiment that we can do. Okay, I have a cricket ball here. I have a cricket ball here which is falling under gravity. Okay, I'll take the initial position as x equal to 0. I'll take x-axis downward. Okay, whatever. Okay, you can do this one. So this has got mass m. It is falling under gravity. You have what you call your acceleration due to gravity. You can find x of t is equal to half gt square. Suppose if you start with 0. Suppose if you take x-axis downward, okay, you can write like this. Yes, speak out. G into t, am I right? So momentum is equal to mg into t, isn't it? Whatever you can write. Now look at here. This is actually you say this is macroscopic, that's why you can apply Newton's second law, isn't it? That's what we said. Now look at here, how I am deviating here. Yeah, okay. So now suppose if you want to observe this one, what you have to do? Suppose if you want to, yeah, again, this follows Newton's second law. How do you verify that one?
I have to observe.
You have to observe. You have to switch on light and you have to put some camera, isn't it? You have to put some camera here, so to observe that one, or something, or you can put some video camera. So that again you can find, you can trace at what time it is there. Okay, you can say at 0 it is started here, after some time where it is there, whether it is following this one or not, isn't it? Or you can take short time and you can find rate of change. Again, you can take short interval, so that you can write dx delta x by delta t, and you can find approximately v of t, isn't it? If you have some video camera. But you can't observe that one in dark, isn't it? If you have video camera, if you're not switching on light, you can't observe that one at all. Okay, you need to switch on light, minimum disturbance that you need to do. Remember again, this light, when it falls on this one, you have some radiation pressure concept, am I right? It will do some disturbance definitely, but whether the disturbance is appreciable or not, that is very important. Here the disturbance is negligible. Because of this radiation pressure, this is not deviating much in its path, or that deviation is negligible, or that disturbance is negligible. Can I say like this? Or make, again, suppose if you are worried about radiation pressure, make light dim, less intense, so that again we have very good what you call camera now, isn't it? So that you minimize the disturbance. Even though you are switching on 100-watt bulb, it will not deviate from its path, isn't it? Your cricket ball, it will not deviate from its path. It will move, and you can verify all of this by using some observation, by using some apparatus, isn't it? We say Newton's laws are verified. Once verified, we can say this follows Newton's second law, isn't it? Any question? I hope that there should be no question here. Wait a second, okay? Now, I have it. Oh.
Why some muted, sir?
No, I better to.
Yeah, okay, sir. Okay.
Yeah, no, I mean, why that is happening, I don't know. It is not because of mic, okay? It's not because of mic. Yeah, Bisham, you better keep your video off. Yeah. No, that's okay. I mean, if you keep your video off, that is good, but it is not good for other because it takes more data, okay? That's the only thing. Now you have electron. I'll make vacuum now. Now here you don't have to make vacuum, okay? Here I have to make vacuum, okay? I don't know whether this experiment can be done or not. As I heard, someone was doing in, I think, Cambridge, okay? This experiment someone was doing in Cambridge for a long time. How electron acted upon by gravity. Okay, this is very difficult because look at the mass, look at the gravitational constant 10 raised to minus 11, capital G, 10 raised to minus 11. Okay, this mass, look at the mass 10 raised to minus 31. Okay, yeah, whatever. This is a thought experiment. Okay, suppose electron is falling under gravity. Again, I'll take this one as x equal to 0. Now again, I'll take this one as G. Again, I'm going to apply F is equal to m into d square x by dt square. Newton's second law give any, it don't give any change, isn't it? It is the same thing. F is equal to m into d square x by dt square. This is m of cricket ball, mass of electron. Now look at here. If you start observing this one, what is the minimum thing that you can do? You have to switch on light. You have to hit electron with a photon. Then it will be so disturbed that it will deviate from its path. If you hit electron with a photon has a momentum. It will transfer some momentum. Okay, suppose if it was falling here, if you hit with a photon, electron may go here, isn't it?
So it is like Compton scattering.
Like that in Compton scattering, recoil, isn't it? So that's why, if you again, yeah, so I say, I'm applying Newton's second law. I say x of t is equal to half gt square. Okay, I say p of t is equal to mgt. Okay, how to verify this one? How to verify this one? You have to switch on light. Once you switch on light, its path is deviated. It will not follow this one at all. There is no possible way of verifying this one.
So as you said in Cambridge, that guy, I mean,
No, he might have done on, again, whether electron falls like that or not, okay? Not observation, obviously. Observation disturbs the system. Now look at here, you make light dim. In this case, suppose if you are observing electron, you make light so dim, less intense, but at least, again, even though it is less intense, it will emit photon, am I right?
Yes.
Again, light emits photon, am I right? That photon should hit on the electron. Then it should be scattered. That scattered photon you need to observe. Then you will get position of the electron, isn't it? Now in that experiment, it is so disturbed that, look at here, it will deviate from its path. There is no possible way of verifying this one. If that is not verified, how do you say it follows Newton's second law?
Yes.
Isn't it? There is no possible way of verifying that one. So maybe that's why we say it will not follow Newton's second law. We don't know whether it follows or not. That's the best idea, isn't it? We don't know whether it follows that or not. But there is no possible way of verifying that one. So that's why what we do is we take on one deviation here. That deviation is like this. Only measurement outcome, we need to design a theory which talks about measurement outcome, not what it is before. This is a classical mechanism which talks about at this time it will be there, isn't it? At this time it will have this momentum. Okay? So this is a kind of deterministic theory. Are you getting my point? Now we can't proceed with that one because there is no possible verification of this one. So position and what you call momentum of the electron. Definitely you can't verify this one at all. Whether it follows this one or not, we don't know. That's why we may say it will not follow Newton's second law. That's also true, okay? Because when we apply classical physics, we can't explain a lot of the phenomena. That's true actually. We can't explain a lot of the phenomena. Are you getting my point? But we don't know whether electron follows Newton's second law or not. But look at the necessity here. Our theory should concern only about measurement outcome, not what it is before. Our theory should be built on measurement outcomes actually. Possible measurement outcome, so probability of getting outcome like that. You can only deal with that one. We have to take deviation from this deterministic theory. Is that clear? Any question here quickly? Thought experiment, okay?
Sir, if we can't verify that, how can we say that classical mechanics is not applicable, sir? We cannot completely ignore classical mechanics.
How do you say it is applicable? I put counter question. You say it is applicable only after verification, isn't it?
Yes, sir.
That's why I said there is no possible way of verifying this one. That's why how do you say it is applicable? It doesn't matter whether it is applicable or not. Even though it is applicable, look at here, you can't verify that one. You can't get anything out of it. And not only that, again, we have seen the experimental phenomena where this failed. No, not only that, where explanation via classical idea failed actually, isn't it? We need deviation. That's already in the 1900 only, we got that idea. Okay. Now, again, how that theory should be, how that new framework should be. That new framework should be on the, again, it should give only the probability of measurement outcome. It can't say anything before. That's why I am not concerned whether electron really follows Newton's second law or not. Anyway, we can't verify that one. Isn't it? Quickly, question, quickly. Because some of these are my words, only to take you towards quantum mechanics, okay? So I'll put this into blog so that we can, allow everyone to comment on that one, so that I can also improve, okay? But this is not disturbing any framework of the theory, okay? I'm very worried about that, okay? Whenever I do something new, it should not disturb the framework of the theory. It should route you towards the proper way, okay? So a part of this idea is taken from Professor I.S. Tyagi book, okay? From IIT Roorkee. Let me mention that book later. Yes, quickly. Any question?
If we do the experiment in a cylindrical chamber, then we can only measure the first state where we are leaving the electron, and we can measure the final state where we are getting the electron, not in between. If we measure in between, it will radiate the electron's path or something.
No, in between we can't say anything.
Yeah, we can only get the result in the final one, where we can get the final velocity of the electron.
Yeah, you can get initial, you can get final, but in between you can't say anything. That's true. That's a good idea. What he's saying this, anyway, that this electron, it will reach here, isn't it?
Yes.
Then try to verify that one. But okay, you verify that one. What happened in between? You can't trace its trajectory like here.
It may follow a straight line or maybe a curve for not straight line, right?
We don't know. We don't know what is its trajectory before, but after measurement you will get that one. That's a good idea.
How do I convince that these will fall to the ground?
No. I mean, what he's saying is, again, you do measurement here at a distance x. Whether it reaches there at that time, just check that out. That's a good idea. But yeah, you did observation. Okay, you found that one. But again, what was happening in this trajectory, you can't verify that one. But you can do that one continuously. You can trace this trajectory continuously. Okay. So now this idea, yes.
Can you predict the path of it?
Okay. Again, wait a second. Again, you are asking. Yeah, that's very good one. Who asked this one? A way of verifying this one, but there is no way of verifying this one.
Sir,
Wait, 1 second. Hold on your doubt. So who asked that one? Can you repeat the question?
Yes, sir.
Again, you are saying that we somewhere it will reach, am I right? We will count the time and all, isn't it?
Between the path, we can say what we can.
No. Yeah, we can. I think we can somehow verify this one. I'll move this one upward. Okay. For one instant of time, I'll keep it here. Other instant of time, I'll keep it here. Keep it here like that. Okay. But I can't verify this one because for this one you need continuous observation.
Excuse me, sir. The moment you make the first observation, you're colliding, or you're forcing the system to collide.
No, I'll take fresh electron, not the same electron. I'll take a fresh electron.
In a string of electrons, we can measure as infinite number of times.
I mean, again. So next, first.
You're colliding the wave function. So any observation made further from that one point of time.
No, I'm not doing the measurement on the same electron. What I do is I'll take fresh electrons. Okay, I'll leave all electron at t equal to 0. I'll measure here. That's a good idea. Okay, that's a good idea. But look at here. To observe momentum also simultaneously. Okay, that's why the uncertainty principle comes actually. Okay, you need to observe that one at least for delta t time, delta x time, isn't it? Then obviously once you hit that one, it will be lost. Once you do the observation, you will be lost. Remember, if you observe, you will get one of the answer always. Okay, if you observe the position, you will get one of the answer. Simultaneously, you will not get momentum. I'll come to that uncertainty principle little later. Okay, next session. Is that okay? Wait a second. I'll come to that uncertainty principle. Yeah, someone is asking. Naren, quickly.
Sir, can you predict the trajectory of the electron?
No, you can predict, but without verification, how do you believe that one? That's what I'm saying. Later you will be convinced, okay? Because of uncertainty principle, you can't have so very well-defined trajectory of electron. Is that okay? Later it will be convinced. But right now, if you are not verifying, how do you say it has a very well-defined trajectory? Is that okay? By taking fresh electron, I think you can verify this one. If you do some, very good arrangement, we don't know. But there is no possible way of doing other one, P is equal to m into V, because for that, you need to do little bit continuous observation. First observation itself disturbs, as he says, isn't it? He said, first observation itself disturbs. Next observation you are doing on disturbed system, isn't it? To find the momentum, you need some repeated measurement, am I right? On the same system. First measurement itself disturbs, deviate the path itself. Next measurement, you are measuring on the disturbed system. Okay. So again, by by taking identically prepared system, different electrons, we can somehow verify this one, but no way of verifying everything. Now look at here. So this whole, yeah.
So I think you can verify this one by using some material. There is a material. Means if electrons stand on that material, then it will light up like that.
No. Then look at here. That material will give some upthrust. Electron will not follow this one. Are you getting my point? If you pass that one through material, it is interacting. Am I right? It is not free fall.
Means when we use some experiment, then we use a collector plate like that.
You are talking about any ionization kind of thing, just like cloud chamber.
There used to be some material. I'm not reminding right now. Something photoluminescent or like.
Yeah, again, photoluminescence. If you take that one, look at here. If photoluminescence happens, it is interacting with that one. Am I right? Definitely, its path will be deviated. Are you getting my point? Or again, its speed will be decreased, or something will happen. Okay, definitely. Without any interaction, you can't have any measurement.
Excuse me.
Yes.
The standard interpretation that has been adopted by most of the academicians around the world is the Copenhagen interpretation of quantum mechanics.
Now wait. We will come to that one later. We'll come to that one later. Okay. a Copenhagen interpretation. We shall come to that one later. Okay, it is there in the first chapter of Clifford. Okay. Now what I am saying is, again, you may think like that. Some photoluminescence, something will help us to track its trajectory, isn't it? But each of that one is interaction of electron with that one. That will definitely disturb its either speed, momentum, or position. Whatever it will be disturbed. Okay. Without disturbing, you can't do the measurement. Inability. Okay. Without disturbing, you can't do the measurement. Is that okay? Now, one thing you need to understand from here, okay? Wait a second, hold your doubt, otherwise it may deviate. One thing you can understand here, what is big, what is small now? Now you can say, where Newton's laws are valid, where Newton's laws are not valid. Can you write down this statement? Okay, wait a second. What is the time, anyone?
7:19.
Oh, I think it is more.
Sir, Shivangshu asked one question.
But it is moved, I think. Yes, what was the question?
Shivangshu asked one question. Sir, can't we apply collision equations of classical mechanics to predict the path?
Once collided, look at here. Okay, you can do one collision. After one collision, its path is disturbed. You need some continuous measurement to observe this velocity, isn't it? So that's a good comment. I think he says, first measurement, collapse that one. Second measurement, you are doing it on collapsed system, isn't it? Disturbed system. Only one measurement, it may give you the position. Okay?
So
Not.
that can also be the definition of big and small. That systems which are not affected by the first
Yeah.
test of observation are big.
Yeah. So that's what I'm. So can you write down what is big and what is small?
Yes.
Where I have written? I thought I have written somewhere here. Yeah. If during the measurement, the minimum, if during the measurement, the minimum possible disturbance on the object is negligible, possible disturbance. If during the measurement, minimum possible disturbance on the object is negligible, then we can call it as big. And classical ideas are valid. Now, if during the measurement the minimum possible disturbance on the object is negligible, if during the measurement the minimum possible disturbance on the object is negligible, then we can call that object as big. Okay? And classical ideas are valid in that situation. That is in this case, tennis ball case. Okay? If a necessary minimum disturbance, okay? I don't know whether grammatically right or not. Necessary minimum disturbance on the object under observation. If necessary minimum disturbance on the object under observation, is not negligible, then we can call it a small. And we cannot apply classical mechanics. I'll try to write notes on this one, okay? So that's very good idea. And one more thing here is, okay, our next theory, should depends on, it can talk only about measurement outcome, possible measurement outcome and probability of them. Isn't it? Look at it. In case of double slit experiment, it convinces that either it will pass through slit 1 or slit 2. You can talk about what is the probability of that it will pass through slit 1 and slit 2. Okay, if you place your source exactly similar to, very symmetrical to both of the slit, then again you will have 50-50 what you call, so possibility, isn't it? Again, you can develop the theory which talks about measurement outcome and probability of measurement outcome, and to verify that one we should have identically prepared system, not again doing the measurement on same system as we did here. Okay, I'll come to this point in the next session. Okay, we shall try to get into uncertainty principle. If we finish out this one, I think from tomorrow we can get into Schrodinger equation. Okay, yeah, I think by 15th we are getting into chapter. It's very good that we started 5 days before. Okay, any more questions? Shall I go offline? I think I'll come by 8 o'clock. Okay, I'll come online back by 8 o'clock. Any questions?
No, sir.
Yeah, anyway, you start discussing, but while discussing, just respect each other's idea. Okay, are you getting my point? I'm saying you are very excited and what you call, you are not respecting one another's ideas. If someone says that is wrong, you should able to what you call convince them politely that it is wrong. Okay, without hurting them. Okay, so again you should learn all of this. Okay, again this is the how to say. Yeah, so any noise in YouTube, I want to do some cross check. No. Yeah, so any noise in YouTube, I want to do some. No. Yeah. Little noise is there, isn't it? Wait a second.
Sir, Akash had asked one question. If we don't observe by photon, we place some nuclear counter. To count electron hits.
No, hits you can measure only position. If you count where it is hitting, you can measure position. Simultaneously, you can't measure the momentum. Classical mechanics means you need to verify both actually.
Yes.
Are you getting my point? Position as well as momentum. Again, after next session, you don't question this one because there is uncertainty, isn't it? You can't measure both simultaneously. There's a natural uncertainty. Not only it's a measurement problem, particle itself cannot be prepared with a state of definite momentum, definite position. That I'll try to convince in the next session. Necessary minimum means, dim light like that. I wanted to say, look, it is disturbing the system, am I right? If I switch on the light, it is disturbing electron. Try to make that disturbance minimum while doing the observation. However minimum you do, it will emit photon, am I right?
Of course.
Photon should hit the electron and then you have to observe the scattered photon to find its position.
In the MIT that was one to say.
No, but yeah, he also talked about electron. Yeah, he applied that one to electron. That's correct. In the next 2 thought experiment, we do the similar thing. Okay, one is thought experiment, other one is the realistic experiment. Okay, we shall do that one. So that I'll try to convince that uncertainty from this measurement, we shall slowly deviate to uncertain. I told one uncertain thing here, uncertain thing that happens, superposition state. Superposition state itself talks about uncertainty. Uncertainty means not position or momentum uncertainty.
Indefinite state.
Indefinite, isn't it? Either slit 1 or slit 2, we don't know. Okay, yeah, I'll come to that one. I'll go offline. I'll come back by 8 o'clock. Okay. Yes.
Is there any joke today?
No more jokes today.